Okay, so let's have a look at some more examples of Faraday's and Lenz's laws. And so, well, the first one is an interesting one where we have a coil moving it's in horizontal plane there, that little rectangular coil that I've drawn, moving into a vertical magnetic field. And it's going to move in at constant velocity. So in other words, we're just going to gradually move that into the field and through and out. So it's quite a common example in textbooks and in questions, crops up as well. And it's important to be able to understand. Well, let's see what's going on and see if we can figure out what might happen in the coil as it goes into the field, through the field and out of the field. So, well, first up, imagine we're looking down from above. So we'll take a sort of top view and sort of redraw the situation. So if that's where we're looking from. Well, then we can imagine that green area is showing the field going kind of into the screen because we're looking down from above. And there we can see our coil flat from above, kind of just about to enter the field. And we'll just kind of track its progress on a graph. So let's see if we can follow a graph of the flux linkage as it progresses along. Well, we can either do the graph against time, but it's going at constant speed. So let's do it against just the distance along, and then we can exactly line it up here with the field above. So there's the sort of two boundaries of the field. Now in reality, the field kind of does some funny things at the edge, but we're going to just ignore that for this. We're just going to imagine a nice uniform field. Okay, so the flux linkage, what's it going to do? Well, you might want to pause and see if you can figure out what the flux linkage might do. But of course it's zero right up until that entry, the front end enters into the field. And then at that moment, well, as it enters in, it's going at a constant speed, remember. So the flux linkage is actually going to build up uniformly against time. So I'm actually going to get a nice straight line there until it's completely into the field. Now, then, when it's inside the field, say in the middle, well, the flux linkage is not going to change. Now, this is interesting. So there's going to be just a constant value. Our line is therefore going to be horizontal. The amount of flux linking through our coil just stays the same until the leading edge is just about to come out of the coil there. Well, we don't need any more diagrams. We know that it's just going to gradually diminish until the complete rectangle is out of the field when the flux linkage is zero again. So hopefully that kind of makes sense. Well, now the strength of this is that we can now decide what a graph of the induced EMF might look like, because we know Faraday and Lenz's law give us that information, because we know that E is minus the rate of change of flux linkage. So again, have a pause and see if you can draw the graph. Well, hopefully you realise that we're only going to get an EMF induced during flux change moments. Well, the only flux change is there and there. This is constant, this is constant, this is constant. So let's see. So, well, in this, the flux linkage is increasing as it enters the field there. As it sort of goes in, we're going to get more and more flux linkage. So we can, therefore, the EMF should be a constant for this rectangular coil during that period. So it's going to go along there, and then at that moment we're just going to get this kind of constant EMF, but it's going to be negative, because now negative we'll see exactly what that means in a minute. So it's going to be sort of negative over that period up until that point. And then there's going to be no EMF again. It's just going to be zero, because there's no change in flux all the way along until it starts to leave the coil. But then we've got a negative gradient, so we're going to get a positive EMF because it's minus minus, and so we're going to get the equal and opposite effect there. And so that's what you get. So it's a kind of interesting graph. It's got a little bit of EMF as it goes in and a little bit of EMF as it goes out. Now let's just look at the directions of that, because it's nice to think about Lenz's law, why that is. Well, as our little rectangle is going into the field there, into the magnetic field, then the flux linkage is going up. So the EMF in the coil has to be in such a direction that the current that flows tries to reverse that. Okay? Well, so let's just see what that might mean. Well, what we're saying is that delta n phi, the change in flux linkage, the flux linkage is increasing. It's going up all the time. So it's positive. It's positive delta n phi or dn phi. And so, well, which direction would a current flow to try and stop that happening? Well, if the current flowed clockwise around, well, you can use, if you use your sort of right hand grip rule, you'll see that it will actually reinforce the field, because you'll end up with a field going down through the coil. That would create a field going down through the coil. Well, then remember that would make the field even stronger. That breaks Lenz's law. Lenz's law says that the EMF is such as to oppose the rate of the change of flux, such as to oppose the flux change creating it. The flux change is increasing. So it's going to try and produce, it's going to flow to produce a field coming up through the screen. So I'm going to try and draw that with dots. So it's going to kind of try and cancel out the increase. The flux is going up that's linking through the coil, so it's going to flow anti-clockwise to kind of have a field coming, make a little field coming out of the screen, which will slightly cancel out or oppose the flux change. So that's why it's a minus, and that's what the minus means. It just gives you the sense of the rotation of the EMF. But you don't actually have to ever work out which direction the EMF is going, by the way. And great, so that's a really nice example. I just want to talk about a few more examples which are really interesting and sometimes crop up in questions as well. Well, this little circuit here, first of all, is we've just got a little power supply and we've got a switch. But here, so we've got two lamps. Now, the first one's in series with a resistor, just a normal resistor. But the second lamp is in series with, well, what is that thing? Well, that's a coil, and those two double lines mean that it's got an iron core, which just makes all the magnetic effects much more powerful. So this is a solenoid with an iron core. Okay, well, what's going to happen when I close the switch? So the idea is that we come along and we just go bang, close the switch. And what's happened? Well, what does happen is really interesting. This lights up first, and then there's a small delay before the second lamp lights up. And the question is, why is that? You know, why is there that delay for the second lamp to light? So this is sometimes called a little delayed lighting circuit. Well, the reason for it is something called a back EMF. Now, it's not usually referred to that in questions, but you just have to discuss it in terms of Faraday and Lenz's law. So let's kind of try and explain that. So, well, when the switch is closed, there's going to be a rapid current growth and a rapid range of change of flux in the coil. But of course, that's cutting across the coil itself. This is why it's called a back EMF. So that's Faraday's law. It means that an EMF will be induced in the coil itself, yeah, because there's a rate of change of flux in the coil, because it's becoming an electromagnet. So that means that, but Lenz, of course, says that that's going to oppose the change creating it, which is the power supply. So it's going to oppose the power supply. We know we can't just suddenly get more power from nowhere. That's what Lenz's law says. And so there's a delay. There's a delay while that happens. There's a momentary delay until the light in the coil comes on. So a really interesting example there. So here's another example, which is a really interesting little demonstration. Well, this little guy in the middle here is a little neon lamp, or it could be some kind of LED. But it's one that neon lamps are usually used because a neon lamp needs a high potential difference in order to light up. You know, it could be 60 volts or 100 volts or something like that. Well, we might only have a 12 volt supply. And the idea is that initially the switch is closed and then the switch is suddenly opened and you get a flash on the neon lamp. Now, why would that be? Well, because of course 12 volts is not enough to light the lamp, so the lamp isn't on at the beginning. But you notice that once again we've got a coil, a solenoid with an iron core there. So, well, what happens this time is that when the switch is opened, then the current that exists in the solenoid, in the coil, just collapses. And of course the magnetic field, therefore, that's through the coil also reduces rapidly to zero. So there's a very rapid rate of change of flux linkage in itself, in the coil itself. Yeah, remember this field is going to cut across itself as it disappears to zero. So well, as that happens, Faraday tells us, because it's a very rapid rate of change of flux, it's going to be a big EMF induced. And we know that if the neon lamp flashes, then we know how big that is. It's going to be big enough to light the neon lamp. Well, the final example, just in this little section, is a DC motor. So, well, we just remind ourselves here, what's going on is, as soon as we close that switch, we'll have a current kind of coming up around the coil, and that we know Fleming's left-hand rule, that'll make the coil spin. But what's an interesting little feature, which is tested in exams, is that what happens to the current after it's switched on? You know, is there any kind of effect because of this rotation of this conductor inside a magnetic field? Well, of course there is. And if we think about it, well, as soon as we switch on, the motor's going to start to spin. And so we've got conductors cutting through magnetic flux. We've got a flux change in the coil. And, well, that's going to induce an EMF in itself again. And of course, that's going to oppose the change creating it. So it's going to kind of create a back EMF, an EMF which opposes the supply. And in other words, a current will flow which opposes the original current that's making it drive. So a bit of a complicated situation, but it makes it a lot clearer if we sort of imagine drawing a graph and say, well, okay, let's suppose that, you know, here is when we switch the motor on. So that's when I close the switch. Well, the current is going to go zooming up to a big value just using I equals V over R. But then as the motor speeds up, that you're going to get a bigger and bigger back EMF. And actually what happens is that has the effect of reducing the current, opposing the current, until it just reaches a stable value. And then that's the sort of normal motor running value. It's actually quite useful for a motor because it means that they heat up less. If you stop a motor rotating, you get quite a bad heating effect because the current's too big. So this is actually a preferable situation for a motor. So I hope this makes sense, and have a go at a few questions which kind of look at a few of these ideas on using Faraday's and Lenz's law.